Single displacement reactions. Here's a generic equation. A displaces B from compound BZ and forms B and compound AZ. That explanation, although correct, likely means nothing at all to you. In order to understand single displacement reactions, you need to learn about oxidation reduction reactions. So the explanation that follows, it's not short, it's about 20 minutes, but you'll need to watch it carefully to understand this. But it's worth the time. Oxidation reduction reactions are the foundation of battery technology and corrosion protection. After this intro, I'll explain the lab procedure and the lab requirements. So the third type of chemical reaction we want to study is that of a single displacement reaction, often called an oxidation reduction reaction or simply a redox reaction for short. This is the most complicated of the 6 types of reactions and will require the most explanation. Let's start with a familiar example. Here is a picture of a clean steel bolt. The surface is clean. That's the color of iron because steel is mostly iron. In the photo on the right, we see a bolt with an oxidized surface, a rusted surface. That orange-brown color is the color of rust. And so chemically, iron 3 oxide, Fe2O3, is what we commonly call rust. What's actually happening during this oxidation or rusting process? I want to focus on the elements, and so this is intentionally not balanced. Well, how about the iron? Now, iron metal has an oxidation state or a charge of 0. All elements are neutral. They all have an oxidation state of 0. But the iron in iron 3 oxide is not metal and is not neutral. It's actually iron plus 3, and that's what the name tells us. It's an iron cation. In going from iron 0 to iron plus 3, has iron gained or lost electrons? Well, the charge is increased by plus 3, and therefore it must have lost negative charges. Losing negative charges means that it lost electrons. And that's what we call oxidation. Iron is being oxidized when it reacts with oxygen. Iron is losing electrons. It's lost 3 electrons to go from 0 to plus 3. So here iron goes to Fe plus 3, releasing 3 electrons. We say that iron is oxidized. Let's look at oxygen. What's happening to it in the process? This element has an oxidation state or charge of 0, but the oxygen in iron 3 oxide is not oxygen. It's actually oxide with a charge of -2. So what's happened to oxygen? Well, it must have gained 2 electrons to gain 2 negative charges, and a gain of electrons is referred to as reduction. So while the iron is being oxidized by the oxygen, the oxidizer, the oxygen itself, is being reduced. So here, focusing on a single oxygen atom, I'm saying 1/2 O2 is a single oxygen atom, gains 2 electrons and forms oxide, and oxygen is being reduced. These 2 processes have to occur simultaneously. You can't have one without the other. If something is losing electrons, like iron is here, then something else must be gaining them, like oxygen is in this case. How will we remember this? Well, here's a mnemonic. Here's a memory aid. Leo the lion says grr. Leo reminds us of the loss of electrons is oxidation. And grr reminds us of gain of electrons is reduction. In single displacement reactions, a metal reacts with a metal cation that is dissolved in water. So if you look at the beaker on the far right, that white salt is zinc sulfate. And when dissolved in water, it forms a clear, colorless solution of zinc ions. And that's the clear solution that the copper metal strip is sitting in. And you can see that there's no reaction. So when a strip of copper metal is placed in a solution of zinc sulfate, no reaction occurs. If we attempted to write an equation, it would look like this. We'd say no reaction. But look at the beakers on the left. The beaker on the far left contains a blue salt, that's copper 2 sulfate. When it's dissolved in water, it produces a clear blue solution of copper 2 ion. And zinc metal is sitting in that. You can see there is a reaction. The surface of the zinc strip has darkened, and that's copper 2 ion has gained electrons. It's been reduced and deposited as copper metal on the surface of the zinc. And at the same time as that's happening, zinc metal has dissolved, it's been oxidized, and gone into solution. So when a strip of zinc is placed in a solution of copper 2 sulfate, copper metal deposits as a black deposit on the surface of the zinc. Copper 2 ion is reduced to copper metal. Simultaneously, zinc is oxidized to zinc plus 2 ions. The reaction equation looks like this. Zinc solid plus copper 2 ion react, producing copper solid and zinc 2 ion. Let's take a look at this reaction. In the clear, colorless solution of zinc sulfate on the right, I'm placing a strip of copper metal. And in the clear, blue solution of copper 2 sulfate on the left, I'm placing a strip of zinc metal. Now there's no reaction on the surface of the copper, but you can see the surface of the zinc immediately starts to darken. After about an hour, you can see the large deposit of copper on the surface of the zinc. In fact, it starts to take on the salmon color of copper. You may also notice that the blue color is fading in solution as more and more copper ion plates out of solution. After several hours, still no reaction on the surface of the copper. Now, the reaction at the surface of the zinc is gone to completion. The solution is colorless. All the copper has plated out of solution. You may also notice that the zinc strip is thinned out as some of it has dissolved in solution. The key to being able to predict these reactions is this next statement. The more reactive metal displaces the less reactive metal's cation from solution. This table is called the activity series of metals and will allow us to predict which combination of metals and metal cations will and will not react. So in the column on the left we have a variety of metals. Notice that each of them is being oxidized as we go left to right. They're all losing electrons in the process. Listed in the second column is the EMF, or the voltage, that is produced if the value is positive above hydrogen. These are favorable. They'll occur spontaneously and produce a voltage. Or they list the potential or voltage that must be applied if the EMF is negative. And that's with reference to when a metal is being oxidized. So let's look again at our example. Zinc being oxidized to zinc plus 2, that's favorable, plus 0.76 volts. Copper being oxidized to copper plus 2, that would be unfavorable, negative 0.34 volts. So active metals, those that are higher on the table, have high positive oxidation potentials, positive values. That means they prefer to exist as ions compared to hydrogen, which is added as a reference, is set to 0, and all the other elements are compared to it. Unreactive metals, those at the bottom, have negative oxidation potentials, and they prefer to exist as the metal compared to hydrogen. So in single displacement reactions, our rule is that the more active metal, the one that's higher on the list, zinc in this case, will displace the less reactive metal's cation from solution. You see, you're never going to have two metals reacting. It's got to be a metal and a metal cation. So let's look at it some more. Zinc is more active. It's higher than copper, and therefore zinc metal will displace copper 2 ion, forcing it to accept electrons and be deposited from solution. As zinc is being oxidized, copper is being reduced. One of the reactions will always proceed left to right. One of them must proceed right to left. So let's write these values down again. Zinc, left to right, oxidation is favorable, plus 0.76 volts. Now in our reaction, remember, we were using blue copper 2 ion in solution, and it was proceeding from right to left. So what we do there is we change the sign from negative to positive whenever you change the direction. So plus 0.34 volts, it's favorable for copper 2 ion to be reduced to copper metal. We then add these two half reactions together. One is oxidation, one is reduction. The electrons will always cancel, and we have zinc solid reacting with copper 2 ion, producing zinc ion and copper metal. And we add the potentials together, it's plus 1.1 volts. And that is favorable. That reaction will proceed as we saw in the video. This is a battery. It's called the Daniell cell. You can use that 1.1 volts to push current and do work for you. The reverse reaction, which is what we tried to do in the beaker on the right, we put copper metal in a zinc ion solution. That will not work. The potential for that reaction, for copper trying to reduce zinc, is negative 1.10 volts. Will not work. Let's get some practice. Report the E0 value, E0 electrode potential, for the following reactions. If a reaction does not occur, write no reaction. If a reaction does occur, complete and balance the equation. Circle what's being oxidized, draw a square around what's being reduced. So here we have aluminum ion reacting with calcium metal. Now let's just ask ourselves, what would the products be if this reacted? Well, the cation would be reduced to the element aluminum, and the metal would be oxidized to some oxidation state. So Al plus 3 becomes the element Al0. If you're not sure what to write for the oxidation state of the metal cation, two ways you could know this. Certainly calcium's in group 2A, and it's the only oxidation state it ever has is plus 2. And if you're not sure, just check the activity series table to see what cation is being formed. All right, so what's happening in the case of aluminum? It's gaining 3 electrons, it's being reduced. How about calcium? Calcium is losing 2 electrons, it's being oxidized. Let's check the activity series table and find out the potentials for these half reactions. In the case of aluminum ion being reduced to aluminum metal, we have to go from right to left, so we need to reverse the sign. The potential will be minus 1.66 volts. That'll be unfavorable for the reduction of aluminum ion to aluminum metal. Look at calcium. It's higher on the list, and in this reaction calcium is being oxidized to calcium plus 2. That's the way this is written from left to right, so we take the value as it sits, plus 2.87 volts. That's very favorable. So we've seen that the reduction of aluminum ion is unfavorable, negative 1.66 volts, but the oxidation of calcium to calcium plus 2 is very favorable, plus 2.87 volts. If you add these two half reaction potentials together, the net is positive 1.21 volts. So in theory at least, that reaction is very favored. Now this equation may look to be balanced, but it's not. It's not balanced in terms of charge. Notice the charge on the right is plus 2. The charge on the left is plus 3. We need to balance the charge as well as the mass. So if I double up on the plus 3, it gives me plus 6, and then I can 3 times plus 2 is plus 6, and now I've balanced the charge. Both sides are plus 6. All it needs to do now is balance the mass. We'll double up on the aluminum and the calcium, and now it's balanced. We're also asked to draw a circle around the species being oxidized. What's losing electrons? Well, it's the metal. The metal is always the species being oxidized. Draw a square around what's being reduced. Well, the cation is going to be reduced. Now the aluminum plus 3 ion in this reaction will have come from dissolving an aluminum salt in water. For example, aluminum sulfate, aluminum nitrate, aluminum chloride. And in these salts, the sulfate, the nitrate, or the chloride, they must be present. They do not take part in the reaction, and so they're called spectator ions. Equations that do not include the spectator ions and show only the reacting species are called net ionic equations. So up here, what we've drawn is a net ionic equation. It shows the guts of what's really happening without all the extra spectator ions. But if we saw this in reality, it might look something like this. We might see aluminum sulfate reacting with calcium, producing aluminum and calcium sulfate. Or perhaps aluminum nitrate with calcium, producing aluminum and calcium nitrate. Or perhaps aluminum chloride and calcium, producing aluminum and calcium chloride. Before I leave this, I need to confess that this reaction, although correct theoretically, is not a realistic one. The truth is that calcium is so reactive that it wouldn't really be you couldn't do this in water. It reacts with water. But I chose to use it just to illustrate the process, and all the other examples that follow are certainly realistic and can be carried out. Well, let's get some more practice. Let's say we take a magnesium ion and attempt to react with hydrogen gas. What products would be formed? Well, magnesium ion would be reduced to the element, and hydrogen would be oxidized to some cation, H+. If you're not sure which ion, look at the activity series table, and you'll see that hydrogen would be oxidized to H+. Now, magnesium ion would be reduced, gaining 2 electrons to form magnesium metal. At the same time, hydrogen, the element, would be oxidized to H+. Let's check the activity series table and see about the favorableness of these reactions. So magnesium ion gaining 2 electrons, going from right to left to being reduced to magnesium, well, that would be unfavorable. We'd have to reverse the sign because we reversed the direction of the reaction, negative 2.36 volts. So when you read the series, left to right, use the value stated. When you go right to left, change the sign. Negative 2.36 volts for the reduction of magnesium ion to magnesium metal. Now hydrogen, either way, is 0 volts. So magnesium, the reduction of magnesium is unfavorable, 2.36 volts. And the oxidation of hydrogen to H+ is 0 volts. If we add those together, the result is negative 2.36 volts. You can see that reaction would not proceed as stated. But that means that the reverse reaction would proceed. In other words, if I took magnesium metal and put it in an acid, H+, it should react. Magnesium would be oxidized to Mg+2, and hydrogen ion would be reduced to hydrogen gas. Now, I've already written this in a balanced form for you. The potential for this reaction would be plus 2.36 volts, so it should work. Now, this is the net ionic equation. I've asked you to circle the element which is being oxidized. It's always the metal that's going to be oxidized, and it's always the cation that's going to be reduced. This is what the reaction might look like in reality. You can't buy H+, but you can get an acid such as hydrochloric acid. So if you put magnesium metal in hydrochloric acid, it should react, producing hydrogen gas and magnesium chloride. Let's view this reaction. The test tube on the left contains hydrochloric acid. The test tube on the right contains magnesium metal turnings. Clearly, reaction is vigorous. Hydrogen ion is being reduced to hydrogen gas. We can test for the presence of hydrogen with a flame. Hydrogen burns with a colorless flame, but it does have a distinct popping sound when burned. Let's look at the next reaction. I have silver ion reacting with copper metal. Well, if this reacts, what will that look like? Well, the silver will be reduced to the element and copper oxidized to copper +2. Again, check the activity series table for the charge of the ion. Silver ion is gaining 1 electron and being reduced to silver metal. Copper metal is being oxidized to copper 2 ion. Let's check the activity series and see if this is favorable or not. Now for silver ion to be reduced, going from right to left to the silver metal, we'd have to reverse the sign. That would be plus 0.80 volts, so it would be favorable to reduce silver ion to silver metal. Copper metal being oxidized to copper plus 2, well, that's unfavorable, negative 0.34 volts. So the reduction of silver ion is favorable, plus 0.8 volts. The oxidation of copper is unfavorable, negative 0.34 volts. The net effect is plus 0.46 volts. This reaction should proceed. Now, it's not balanced as it stands. We have plus 1 charge on the left and plus 2 on the right, so let's double up on the silver ion that balances the charge, and then let's balance the masses as well. Now we're asked to put a circle around the element being oxidized. That would be the metal is always oxidized and the ion is reduced. We'll put a square around that. This is then the balanced net ionic equation. What might that look like in real life? Well, for example, we can't get silver ion by itself, but we could use silver nitrate and copper. And the silver ion in silver nitrate would be reduced to silver metal, and the copper would be oxidized to copper 2 nitrate. Let's take a look at this reaction. Here a strip of polished copper metal is placed in a beaker of silver nitrate solution. Notice that the surface of the copper immediately starts to darken. What's happening? Well, silver ion is being reduced to silver metal, and silver metal is plating on the surface of the copper. After several hours, the reaction has come to completion, and all of the silver that was in solution has plated out as silver metal. Notice the solution has turned blue as some of the copper has oxidized to copper 2 ion and is now in solution. Before we look at the lab procedure, I'd like to show you 2 short video clips that are informative but also fun. Take a look at the metals that lie above this double line. Lithium, potassium, barium, calcium, and sodium. They are such strong reducing agents that they will even reduce water to liberate hydrogen gas and hydroxide ion. Let's take a look first at lithium metal in water. The beaker contains tap water. I'll add some universal indicators so we can monitor the pH change during the reaction. Universal indicator is green at pH 7 and it turns purple in a base. This is lithium metal. It's stored in oil to minimize oxidation from the air. The surface that's somewhat oxidized has a grayish color, but a freshly cut or exposed piece looks silvery white, as most metals do. Lithium is the least dense of all the metals. Its density is only 0.53 grams per milliliter, so it's roughly half the density of water, so it should float. It's just soft enough that I can cut it with this spatula. It definitely floats. The indicator's turning purple as hydroxide is released during the reaction. And you see the gas released? That's hydrogen gas, so it should ignite. Now hydrogen gas burns with a colorless flame. When I turn off the lights in the fume hood, you'll see that this flame is pink. Why is that? That's actually lithium ion being carried up from solution and burned in the flame. So water is reduced to hydrogen gas and hydroxide ion. The hydroxide ion turns the indicator purple.
Pretty vigorous reaction. Let's take a look at the reaction of sodium in water. And just like lithium, it will reduce water, liberating hydrogen gas and hydroxide ion. Looking at the activity series, you might think that sodium won't react as readily as lithium because lithium has a higher reduction potential compared to sodium. But in fact, the reaction with sodium goes more rapidly, likely because sodium has a lower melting point. The heat of the reaction will melt the sodium quickly, exposing more surface area to the water, and so the reaction is more vigorous. Let's take a look at this reaction. So we'll start as before with tap water and universal indicator. pH is neutral to start. Sodium metal stored in oil. Now, sodium metal is just slightly less dense than water. Its density is 0.97 grams per milliliter, so it should still float. A little softer than lithium, so it's easier to cut with the spatula to expose fresh surface. I better move that bottle out of the way just in case. Wow, the heat of the reaction ignited the hydrogen. It's burning with a yellow-orange flame. What's that from? Well, that's sodium ion carried up into the flame. It's quite a bit more vigorous than lithium, isn't it? It's almost terrifying. If I'd put a larger piece in there, I'd have broken the beaker for sure. I've done that a couple times inadvertently. So, sodium reduced water to hydrogen gas and hydroxide ion. Pretty strong reducing agent.
Here's the setup for the activity series of metals experiment. I have a plastic plate with 24 wells in it. So there are 4 columns of 6 horizontal rows. These are the metals we'll use: zinc, lead, magnesium, and copper. We'll put the metals in the vertical columns: zinc in the first column, lead in the second, copper in the third, magnesium in the fourth column. And then we'll add ions of metals across each row. So silver plus 1 ion across the first row, copper plus 2 ion in the second row, magnesium plus 2 ion across the third, zinc plus 2 ion across the fourth, lead 2 ion solution across the fifth, and hydrogen ion from dilute hydrochloric acid across the sixth row. So here I've added the metals: zinc in the first column, lead in the second, copper in the third, magnesium in the fourth. The next step is to add the solutions of these cations, and we'll do that next. I've sped this up for sake of time. If I had 2 hands free, I'd hold that dispensing bottle closer to the well plates. Okay, silver plus 1 cation is being added to the first row, a solution of copper 2 cation to the second row, a solution of magnesium plus 2 cation is added to the third row, a solution of zinc plus 2 cation is added to the fourth row, a solution of lead plus 2 cation is added to the fifth row, and to the sixth row we'll add 1 molar HCl, which should react pretty quickly with the zinc, and particularly with the magnesium, because magnesium is so high in the activity series. Wow, look at magnesium go in the lower right corner. The magnesium's already dissolved. I put another piece of magnesium in just to show you the reactivity. On the far left you see that zinc is reacting, slowly evolving hydrogen. Copper and lead not so much. Copper is below hydrogen on the activity series, so we don't expect it to react.
Some time has elapsed. Let's record some observations. Look across the first row. We see a deposit has formed on the surface of all four metals, zinc, lead, copper, and magnesium. That deposit is silver metal. Silver cation was reduced to silver metal by all four of these metals. This is what we expect. Recall that metals that are higher on the activity series will reduce the cations of metals that are lower on the activity series. Take a look at the second row. Is copper 2 ion depositing on the surface of any of these metals? Clearly you can see a black deposit on the surface of the zinc, and I can see a deposit of copper on the surface of the magnesium. We should also see a deposit of copper on the surface of the lead, because lead is higher on the activity series than copper is. Now this reaction would be slow because lead is only slightly higher than copper. In fact, it is quite sluggish. We don't expect to see any reaction for copper metal with copper ion. So again, recall, metals that are higher on the activity series will reduce the metal cations of a metal that is lower on the activity series. Take a look at the third row where magnesium sits. We don't see any deposit except perhaps on the lead, and that isn't a deposit, it's just the way the camera took the picture. We shouldn't see any deposit of magnesium on any of these metals because magnesium is the highest on the activity series. Magnesium in fact prefers to exist as a cation in this form rather than be deposited. Zinc is the second highest on the activity series, and therefore its cation should only be reduced by magnesium, which is what we see. The zinc cation is not reduced by copper or lead or zinc. Lead plus 2 is rather medium to low on the activity series. It would be reduced by any metal that's higher on the activity series, such as zinc and magnesium. It won't react with itself, and certainly copper cannot reduce lead plus 2 ion. Hydrogen ion is below zinc and magnesium on the activity series. It's also below lead, but only slightly so. The voltages are almost the same, and so this would be an extremely slow reaction of lead dissolving and reducing hydrogen ion to hydrogen gas. Copper sits below hydrogen on the activity series and should not, therefore, be able to reduce hydrogen ion. So that's the end of the activity series experiment. There are some equations related to this for you to balance in the lab report. But before we finish, I just want to look at one more reaction that's quite instructive. I've got a piece of copper metal in the test tube. On top of it, I'm going to put some 1:1 nitric acid. Now, nitric acid should not react with copper. Recall that copper is below hydrogen on the activity series, and therefore it should not be oxidized and reduce hydrogen ion to hydrogen gas. But in fact, it reacts quite vigorously. Take a look. The solution is turning blue. That copper is dissolving. It's being oxidized. Furthermore, a lot of gas is given off. I see a brown vapor. That brown vapor is nitrogen dioxide, NO2, and it is an acidic oxide. This wetted piece of pH paper shows the tip turning distinctly pink or purple, indicating the gas is acidic. I'll hold it against the scale on the pH paper container. You can see that the pH lies between 1 and 2. Notice the copper metal is completely dissolved. That was a vigorous reaction. So what happened here? Recall that hydrochloric acid did not react with copper, but nitric acid is dissolving it. So it isn't the hydrogen in the acids that's reacting with the copper. In the case of nitric acid, it's the nitrogen. Nitrogen is in its highest oxidation state, +5, and in acidic solution, in nitric acid, it's a strong oxidizer, and that's what's taking electrons from the copper. Compare hydrogen chloride. In hydrogen chloride, the chloride ion
is in its lowest possible oxidation state. It doesn't need any more electrons.
So with respect to the lab report, you have a table to include with your observations, for example, no reaction or reaction. You can also record changes in appearance. Note that all of these solutions listed in the leftmost column are strong electrolytes, meaning that they would separate into ions in solution. So for example, silver nitrate in solution forms silver cations and nitrate anions. Then you have some questions to answer. Based on the observations, list the 4 metals tested in order from most reactive to least reactive. If you're not sure, check the activity series. Where would both silver and hydrogen fit on this list? If you're not sure, check the activity series. And finally, question 2, include the completed equations that are listed on the next page and write them in net ionic equation form. If no reaction should have occurred, then just write no reaction. But if a reaction should have occurred, then please complete the equation and balance it for both charge and mass. And the first equation has been completed as an example. Let's take a look. So in the first case, zinc metal reduced silver cation to silver metal, and in the process, zinc metal was oxidized to zinc plus 2 cation. This equation is balanced for charge and mass. 0 and plus 2 charge is equivalent to plus 2 and 0 charge. Note that we did not include the nitrate ion. Those are spectator ions, and we're only showing the net ionic equations. So you can complete the rest of these in similar fashion. And that should be enough for this experiment. Thanks for watching.